Okay, for this exercise, we're going to hit upload on the left, hit browse, navigate to the TD2 folder, and then open up cats versus dogs. So here we're going to build a classifier. Since we'll be using a JSON dataset sourced by a URL right here, we don't need to upload any dataset file for this exercise like last time. We're also going to take a dataset full of images of cats and dogs and then split them into a training and testing set. We do this to test the machine on data it's never seen before after it's finished training. And this kind of learning is supervised learning, as it trains on many labeled examples of what a cat is, what a dog is, and attempts to find a model that minimizes loss. So in this case, how accurate it is to getting the prediction correct. We'll first start by importing libraries and packages. Click execute the cell. And it's important to note that we imported the image data generator from the Keras package that we'll be using later. Now, I had mentioned earlier the dataset we'll be using as a JSON dataset sourced by this URL. But if it doesn't work, we're going to follow the instructions here by hitting Control, click, navigate to this tab, scroll down, and then right-click, click here, download manually to copy the link address. Now, if your computer automatically downloads a zip file, all you need to do is press the pause button here, and then it will pause any downloads that you may have. Go ahead and navigate out of this tab, cut all this out, and then paste the new link in. Run the cell. It may take a while, but once the dataset has finished loading into the notebook, you can see how many images of each we have. So run this, and quick math, 12,501 of each, and then adding both together gives us 2502 images altogether. And now to understand the next part, I'm going to have to go over the logic behind directories using cats and dogs. So we have one dataset that contains both images of cats and dogs. And then we need to split these images into two. One for training the machine, and then one for testing the machine with data it's never seen before. In the training directory, it needs to have images of cats and images of dogs. And each of them are subdirectories. A subdirectory of cats and subdirectories of dogs. Now you can apply this concept to the testing directory. So in total, we have one dataset, images of cats and dogs, two directories, training directory and testing directory, and four subdirectories, two for training, containing one of cats and one for dogs, and then two for testing, one for cats and one for dogs. So in the next cell, go ahead and run it. And this just shows the format of the directories I had mentioned. So one image dataset, two directories, training and testing, and then four subdirectories, cats and dogs for training, and then cats and dogs for testing. Now it's time to split the data, and we'll split it among training and testing. And then we're going to split it with a split size of 0.9. So this leaves 90% of the image dataset for training purposes, and then the remaining 10% for testing. Inside this if-else statement inside the for loop, we are going to be familiar with this since we learned this inside TD1. And basically for each file in this directory, if its length is greater than 0, we're going to append its file name. Else, if their length is 0, it kind of indicates that the data is corrupt, and so we're going to ignore them, and then we're going to print out file name is 0 length, so ignoring. Shuffled set will make the image split randomly, and here we're just defining variables with their lengths for later uses. So go ahead and run the cell. and see that we have 2 corrupt files with 0 length, so we're ignoring them. Now this next line is not very necessary, it's just printing out the length of each list directory. So if you run the cell, it'll give you 90% of training sets and 10% of the total image data set for testing. So these numbers seem right. Now remember when we were talking about neural networks, layers, and dense layers, this is just in code form. So this one specifically is a convolutional neural network, which is a kind of network that's specifically used for image recognition and processing of pixel data. And these layers can be defined with a number of parameters, as seen here. What the numbers mean here is that when it's passed into the first convolutional layer, the first layer will learn 16 3x3 filters, an input shape of, remember we specified 100 by 150 pixels, and a 3-color channel in RGB. So the 16 filters here will first be random, and then the best filters to use for either cats or dogs will be learned over time by the machine. And each of these convolutional layers is paired with a max pooling layer, which is just used to reduce spatial dimensions that are outputted from the convolutional layer, while retaining the most important features. That way the machine can identify specific features it finds that can distinguish cats and dogs from one another. And these layers can be stacked on top of one another inside a dense network. Since there's 3 convolutional layers, the results from the 16 filters for the first layer will be put into the first max pooling layer, and then results from this will then again be filtered 32 times over inside the second convolutional layer, put into the second max pooling layer. Results will then be filtered 64 times over inside the convolutional layer of the third one, max pooled, and then it will get flattened out to convert the data into a one-dimensional array for inputting it into the next layer, the dense layer. So a dense layer is a simple layer of neurons in which each neuron receives input from all the neurons in the previous layer. But here we use an exception which only needs one neuron, given that we use the sigma activation function. And so we're going to compile all this information into the optimizer RMS prop and at this learning rate. And then the loss is set to binary since we only have 2 classes. And then we're going to run the cell. And then we're going to normalize the data. This just means we're going to rescale the images. And to do this, we're going to divide the values by 255. And this turns the values from 0 to 255 into a value between 0 and 1. And then we're going to assign all this to a variable called train data gen. And then the flow from directory will have a bunch of parameters passed through it right here to be able to get to the subdirectories of cats and dogs inside the training directory. So the first one will be the training directory, seen as training dir, and then the next line will be batch size, which is ours is 250, and we're going to use this to load images into our neural network. This can be any number, but it's just good to have one that divides evenly into a step size, which we'll use later. So for example, if we have 20,000 images of cats and dogs, and we choose to set aside 80% of the images for training, it'll take 80 steps to load it into our neural network, since we identified ours as a batch of 250. So quick math, 20,000 images divided by a batch of 250 is 80 steps. Okay, and because images don't all come in one size, we need to change them all into a consistent size, since layers in a neural network need to work in the same dimensions. So here we have our target size set to 150 by 150, and all this is the same for testing and validating directory. Now run the cell. We're going to train the network by first letting it know that the train generator and the validation data generator are the data sources, and then we're going to identify the steps per epoch here, and then epochs here. And then remember back to when we talked about batch size. So steps per epoch should be calculated by dividing the amount of images by batch size, which ours is 250. So quick math, when we first saw each subdirectory, when we printed it out to see the length of each I'll just show it here. So 11,250 for cats, 11,250 for dogs. So total is 22,500. And so if we divide 22,500 divided by our bat size 250, we get 90 steps. Okay? Now before you run the cell, just click up on runtime and then click change runtime type and make sure GPU is selected. Click save, just so that when we run the cell, it'll go by a lot quicker. So the accuracy for training is 92%, and then the accuracy for testing is 81%. So see it visually by running this cell. So it will plot accuracy and loss into two separate charts. So you can see testing accuracy against training accuracy here, and then testing loss against training loss here. You can also test an image of your own. So all you need to do is run the cell. Click on choose files, and then you'll be able to upload multiple images at once by holding Control while selecting your files. Now this machine still has some ways to go in terms of accuracy, but for examples, they correctly identified and classified each example. So this one was a cat example, dog example, and dog example. So go ahead and take a screenshot of these results and then paste them into your answer sheet.